of this session is Mario García Fernández from Universidad Autónoma de Madrid, and he will be speaking on the generalized Richie Flow.
Okay, so do you hear me properly? Is this good?
Yes.
Okay, so
yes.
Thank you, Alfonso, and thank you very much to the organizers, especially to Ronald, for inviting me to give this talk at the conference. I would like to first express my apologies to the rest of the speakers because I was barely not able to attend any of the lectures, only the one by Alfonso. But this week was really inconvenient for me because the workshop is taking place during the ski trip of my kids, so it was not very good. But anyway, I made it to at least to Alfonso's talk. So sorry, especially to Andrea and Marcos. Anyway, so I managed to make it. I'm in Benasque. This is Pere Pascual, who is a famous Spanish physicist, and I'm also, I would like to express my gratitude to the Center of Science Pere Pascual for letting me give this talk in one of the rooms, because the other option was to give it in the tent or the caravan where we are here after skiing. So anyway, thank you so much. Since I'm the last speaker, I guess we should thank the organizer for organizing this nice event. So thank you very much. And let me now start. So I'm going to talk about some joint work with Jeff Streets from University of California, Irvine, and it's about a generalization of the famous Richie Flow. So let me start with something very basic, because I guess the audience is very diverse. Okay, so we should run now. Okay, so if you are interested in the problem of finding the best shape or the best metric of a manifold, then one possibility is to put a metric on it and then to evolve this metric by some nice evolution equation. And ideally, you would expect that your equation is super nice, so that your flow line exists for all time and converges to some preferred geometry. So here, this is a picture of how some manifold is evolving to the round metric on the sphere. Typically, things do not go so nicely because the flow lines may not converge. They may develop singularities, but these singularities may actually be helpful for detecting the topology of the manifold. Okay, so these RDS are very well known since the work of Perelman and Hamilton in the 80s, 90s, 20s, and 2000s, right? Okay, so the most well-known evolution equation for a metric, possibly, is the so-called Richie Flow, which was introduced by Hamilton in 1982. And this is an evolution equation where the time derivative of the metric evolves by -2 the Ricci tensor of the remaining metric. And recall that the Ricci tensor is calculated naturally out of the metric, taking a suitable trace, this one here, in components of the Riemann curvature tensor of the remaining metric. So to get a flavor on how these equations look like, if you choose local harmonic coordinates at some specific time t for the corresponding metric, then if you look at the components of the metric, you are in coordinates. So your metric is just some n cross n matrix of functions. Then the components of this matrix evolve essentially by the heat equation. So the derivative of the component is the Laplacian of the component plus some lower order terms, some quadratic terms which depend on the components and the first derivative. And here, this delta is the Laplace-Bertrami operator, which you can cook up like this in your coordinate patch. So the first or the starting point for the theory of Richie Flow is this theorem by Hamilton and de Turk in the 80s, which tells you that this is a well-posed problem, meaning that if you start with some compact Riemannian manifold, G0, then this evolution equation, the Richie Flow equation, has a unique solution for a small time with initial condition G0. Okay, so at least if you want to use this PDE for finding the best possible metric in a manifold, at least you can start the program. Okay, you can start evolving the metric if your manifold is compact. If you take a look on this expression in components in harmonic coordinates around some specific time t, then we get a flavor or an idea of what is doing on the manifold. So this equation is very similar to the heat equation, and if you think of what the heat equation does to, if you think of problem where you have some how do you say this, varilla, whatever the name of this is in
a bar, the bar.
Yeah, a bar, a metallic bar, and then you have some distribution of heat on this bar. Then at times evolves, the heat tends to become uniform along the bar, right? And Richie Flow has the same effect on curvature. So when time evolves, what happens is that your manifold tends to be more and more homogeneous in the sense of having constant sectional curvature as much as the topology allows. Okay. And what happens is that typically there is some tension, and depending in which region of the manifold you are, sometimes the topology does not allow your flow, your metric to flow to some constant sectional curvature metric. And what happens is that this splits or breaks your manifold into pieces, and via the developing of suitable singularities. This idea is actually this phenomenon is very fruitful because it detects the topology of M, and this was the idea implemented by Hamilton and later by Perelman to solve the famous geometrization conjecture for free manifolds in the 2000s. And I guess this is possibly familiar, at least the story to part of the audience. And sometimes, or maybe what people don't know, is that part of the tools that Perelman was using for making this breakthrough in the Thurston geometrization conjecture come from the theory of sigma models in physics. So he was bringing some of the tools that were used for the study of sigma models in physics and doing a very thoughtful study of these quantities, and then getting some mathematical results. So here, the direction where this goes is kind of opposite to the spirit of the conference. It's not math applied to science, but it's actually theoretical physics applied to math. Anyway. So what I'm going to talk about the rest of my lecture is some generalization of the Richie Flow, which actually fits into this setup that Perelman was studying when he brought in some of the ideas coming from physics. And it's actually a natural evolution equation motivated by the theory of sigma models in physics. So let me tell you what this is. So the additional piece of information essentially is a free form on the manifold which is closed. Okay. So instead of just fixing a smooth manifold compact, say, you also fix some cohomology class in degree. Okay. And then the generalized Richie flow is defined for a one parameter family of metrics GT. Let me say that they are Riemannian. You can consider other cases. And then a one parameter family of two forms. This is the new ingredient of the flow. And these are the evolution equations. So what is H? So I told you that I fixed some degree 3 class in particular if it's some H naught, which is D closed, and the H is some time-dependent freeform, which is closed and evolves by H0 plus dBt. Okay, and these are the equations that you impose. The time derivative of the metric is -2 times the Ricci plus some additional term. And this is essentially the unique symmetric 2 tensor that you can cook up out of a freeform using a metric. You contract to indices. Okay, you take 2 copies of the freeform, contract to indices. And this thing here is the adjoint of the differential operator, of the stereo differential. Sorry. So in particular, if you take D in this second equation, you see immediately that the evolution equation for H is the heat equation. So the derivative of H in time is the Laplacian, okay, or minus the Laplacian depending on your convention. Okay, so this is my notation for H squared, this symmetric tensor, and this star can be written like this in terms of the Leibniz beta connection and an orthonormal frame. Okay, so why study this? So let me explain a little bit about the physical motivation of the equations. So as I mentioned, they come from the study of two-dimensional sigma models in physics. What is this? Two-dimensional sigma model is some physical theory, some field theory, where you consider some background geometry, which is given precisely by a smooth manifold, a two-form, and a three-form. A smooth manifold, a metric, and a two-form. Sorry. And then the fields are maps from the surface into the background, into M. And the Lagrangian is given by this expression. So you take one of these maps, and then you calculate the energy of the map. So the norm squared, the L2 norm of the differential of the map, plus the pullback of the two form via this map into M. And the way physicists think is that the critical points are trajectories for one-dimensional strings in the map, moving or propagating. For me to have this interpretation, you really need to work with a Lorentz signature, but here I'm going to work with the Lorentz signature. If you want to think in terms of this is like a higher or a 2 version of something that is more familiar in 1 dimensions, which is the theory for magnetic geodesics. Instead of thinking of this setup where you have fields going from a surface into M, you can consider just trajectories of point particles on a Riemannian manifold, where in addition you have fixed a magnetic field, which is say an exact 2-form D of A. Okay, and then the natural Lagrangian takes the trajectory gamma, which is a curve, to the integral, to the length of the curve with respect to the metric, plus the pullback of this A, which is like the gauge potential for the magnetic field. Okay. And this is like a 2-dimensional analog of this story. Okay, so far so good. So how does this generalized Richie flow appears? Well, the theory is a bit, the story is a bit complicated, but let me say that physicists try to quantize this type of sigma models, and they run into trouble, and they need to keep track of changes of scale via something called the renormalization group flow. And this renormalization group flow turns out to be equivalent to the equation that I wrote before. Okay, so this is these are equations for the background geometry, which try to keep track of changes of scale when you quantize the sigma model. There is another ingredient which plays an important role in the theory. Let me mention it, even though it's not going to appear very explicitly. But part of this quantization business involves introducing a new field, which is called the dilaton field, which is a function, a smooth function on the manifold. So in addition to to the metric, the two form, you also have this function, which is there. And it has its own evolution equation. Let me say that this evolution equation and even this dilaton field is quite a mystery, and it has many interesting. I mean, there is a very interesting mathematical theory behind it, which is yet to be discovered. And now you can regard these stationary points for the flow as a suitable conformability. And there is some natural action here, says that essentially, and what I'm going to say is not true, but essentially, the generalized Ricci flow appears as the gradient flow for this function. And I'm saying that this is not true because really, in order for this to be true, you need to consider another quantity, which is like the minimum of this over all the functions which integrate to one. And that function is what really gives you the generalized Ricci flow as a gradient flow. So as I mentioned, Perelman was secretly knew about this story, even though he didn't say anything about his papers. And actually, if you forget about the free form, and I mean, from this expression here, which was known to physicists, you do some integration by parts, you get to this expression, and this is precisely the so-called Perelman energy function that he uses in the study of Ricci flow. Okay, you need to drop this norm h squared term. This is what he was using, and it's super interesting that this dilaton field plays a super important role in the theory of Perelman. It's something which really keeps track. It helps to understand the singularities of the Ricci flow in the study of Freeman. Anyway, so with this motivation, let me just go to the mathematical problem. And if Ricci flow is something nice and interesting, why not these other equations which are a bit more general, right? These equations are not just random. As I said, they are motivated by physics, and also there is a hope that they help us in understanding another important problem in mathematics, which is the classification of complex surfaces, which is an open problem by now. So the idea, morally, is that at least when you have a complex structure which is compatible with a metric, these evolution equations help us in the classification of such in real dimension 4 or complex dimension. And there is a nice proposal, specific proposal by Jeff Strips in this paper in 2020. So, of course, naively, we have some more flexible equations because we have introduced more parameters. So this may be useful, and the parameters are not there just in a very random way. They are motivated by this. So let me try to illustrate this in terms of some mathematical, very basic result. Okay, so can we then use to find can we use this thing to find canonical geometries in a more broader class of manifolds than the ones which are dictated by Ricci? Okay, so in order to do this, the first thing I'm going to consider are fixed points for the flow. So let's say that we have a solution of this generalized Ricci flow where the where the metric and the two form do not evolve, right? And then these equations are just this equals to 0, this equals to 0. Okay, does this give us more flexibility? So for the Ricci flow, the stationary points are Ricci flat metrics. Okay, in particular, they are Einstein. And then there is this term by Berger from the 60s, which tells you that if a compact 4-dimensional smooth manifold admits an Einstein metric, then the Euler characteristic of this manifold must be non-negative. Furthermore, if the Euler characteristic is 0, then this is equivalent to G being flat. Okay, so having a Ricci flat metric, Riemannian metric, gives you some strong constraints on the topology, at least for 4-dimensional manifolds. Okay, so this is a particular case of the so-called Hitch entropy inequality, if you know. So let's take one very basic example. Just take a product of two spheres, S3 cross S1. Okay. This manifold has Euler characteristic equals to 0, and therefore it cannot admit an Einstein metric by the previous results, right? Because if this were true, then it would be covered by a torus. Okay, this is not the case. Okay, by this result, if this had a Ricci flat metric, it will be flat. Okay, it will be finally covered by a torus. So it makes no or R4, sorry, makes no sense. Okay, so this already tells you that there are some nice examples of manifolds where we cannot put a nice geometry using Einstein metrics. So what about the situation for generalized Ricci flow? So if we have a stationary point for the flow, this is just given by this system of equations, which we call generalized Ricci flat metrics. Okay. One interesting observation is that this equation corresponds to the vanishing of the Ricci tensor for a metric, sorry, for a connection which is compatible with the metric, but it is not the Levi-Civita connection. It has a skew symmetric torsion given precisely by H. Okay, so instead of considering the Levi-Civita connection in defining the Ricci form, you take this other connection and take the curvature and take the same sort of trace that you use. This gives you a notion of Ricci tensor, but now since this connection has torsion, the Ricci has both symmetric and non-symmetric parts. Okay, so it has both symmetric and skew parts. So the symmetric part of this Ricci is this left-hand side on this equation, and the skew symmetric part is this. Okay. And yeah, another comment which gives you a flavor on what is going on here in terms of curvature. So this tensor, this is a symmetric tensor. This is semi-positive, meaning that if I plug in the same vector 2 times in this tensor, it gives me something which is non-negative. Okay? And therefore, morally, if I have a solution to this, the curvature has to be positive, a bit positive. Okay. So we may actually have solutions on manifolds which have positive curvature. So then let me give you an example for this. If you take M to be precisely S3 cross S1, so recall that S3 cross S1 does not have any Ricci flat metrics. We can identify this with SU2 cross U1. Take these generators for the Lie algebra with these relations. So here E23, for example, means E2 wedge 3. And the E super I's are the dual elements in the Lie algebra. So the elements in the dual Lie algebra. Sorry, if I have E1, E2, E3, E4 a basis for the Lie algebra, then the upper indices means in the dual. Then we can take this free form H, which is just the Cartan free form on the SU2 factor. And the invariant metric G actually turns out to define a solution of these generalized Ricci flat equations. So the reason this is true is via precisely the characterization of these generalized Ricci flat equations via the connection with torsion H. So what happens with this example is that it is a particular case of a much more general class of examples, which are compact simple groups endowed with the invariant metric and the Cartan free form. So the Cartan free form on a compact simple group is always is always closed. And then you take the invariant metric, this pair GH gives you a connection Laplace which is flat, and in particular is Ricci flat, and therefore these equations are satisfied. Okay. So it's a very specific situation of a much more general setup. But anyway, we have been able, via these other more flexible equations, we have been able to geometrize a 3x1, right? To put a preferred geometry there. Yeah, so this is supposed to be useful because it's more flexible. Okay, so what about non-constant solutions of generalized Ricci flows? In the end, we are interested in this evolution equation. So what happens for the general theory? So the first existence results is due to Jeff Stritz in 2008. He proved that this is a well-posed problem, and meaning, as before, that if you give me a specific compact Riemannian manifold endowed with a closed free form, then the generalized Ricci flow exists on a small time with this initial data, okay, with B0 equals 0. And recall that the H is H naught plus D of B, okay, which is evolving with time. So at least, as before, we can try to use these two, generalized Ricci flow tool, in order to find best geometries, or to say something about the topology of a more general class of manifolds, maybe 4-dimensional manifolds. Okay, so I'm going to skip the proof here. So let me give you an example. Okay. So consider the 3-dimensional sphere. Okay, with a round metric. So this has constant sectional curvature 1. Then I'm going to consider a special ansatz for solving the generalized Ricci flow, which is very simple. For any lambda t and eta t, one parameter families of constants, so these are just real functions, define GTHT to be the rescaling by lambda of the round metric on the 3 sphere, and the rescaling by eta of the volume on the 3 sphere. Okay, of course, since we are in 3 dimensions, this is closed, so there is nothing to do. With this ansatz, one can prove that the generalized Ricci flow implies that the eta is constant. So the class here, we're in a 3-dimensional manifold. So the class of the 3 form is the same as the volume. Okay, and the class of the 3 form was fixed, so this means that the volume is fixed. And then writing explicitly the other equation, one can show that the evolution equation with this ansatz reduces to this ODE. Okay, a very explicit ordinary differential equation. So in the case eta 0 equals to 0, this is the case where there is no 3 form present. Then this reduces to the ordinary Ricci flow. And with this ansatz, we obtain the simple ODE, just partial lambda with respect to t equals to -4. So the solution to the flow exists in a finite interval and collapses the 3 sphere to a point in finite time. Okay, so develops a singularity, which is very simple, just collapses everything to a point. Okay, so what happens with the 3 form is present? So if the initial 3 form is non-zero, then there is a unique fixed point for this ODE, given by lambda equals to norm of eta 0 divided by 2, and this is attractive. So my initial lambda is smaller than this quantity, the derivative is going to be positive, and with this condition it's going to be negative. Okay. And then it's not difficult to show that for any choice of lambda, the solution actually exists of this ODE exists for all time, and lambda d converges as t goes to infinity to the value which precisely gives you the stationary point. So somehow, or morally, the idea is that the presence of this H is kind of making the singularities milder under the Ricci flow, okay, for this generalized Ricci flow. Okay, so let me give you one problem which we are not able to solve yet. As you see, this is very concrete, and it can be written in terms of Lie groups. So you can take your favorite left invariant metric and try to prove it. So say that you have a compact semi-simple Lie group with invariant metric G infinity. Then given G0 a left invariant metric and H naught to be this free form, then the generalized Ricci flow with initial condition G naught H naught exists on 0 infinity and converges to G infinity H naught. Okay. Yeah, that's correct. Okay, so you take the invariant metric G infinity. Now you start with any other left invariant metric, and this is just the Cartan 3 form in the group. And then the conjecture is that the generalized Ricci flow with this initial condition is going to converge to G infinity H naught. Okay, so I wanted just to illustrate how little we know about this story, okay? Because this is really a very simple situation, and it's actually complicated to make sense of, or to prove this, even in low dimensional cases. So for the case SU2 with G naught to be lambda times G infinity, this is the previous example that I showed. Okay. And now one can try to prove this thing. It's not so complicated to see. If you can go to the book that I wrote with Jeff to see that if G naught is a diagonal left invariant metric in an orthonormal basis for G infinity, then actually this conjecture holds, and it reduces to a system of ODE. Okay. Okay, so the next thing I wanted to tell you about is a proof of this conjecture in a very simple case. SU2 cross U1. Okay, this is precisely the manifold that I presented before, regarded as a group manifold. So even for the case of SU2 cross U1, this result was not known until last year. Okay, and we prove it, and the way we prove it is interesting because it uses complex geometry. We consider a specific type of the generalized Ricci flow, which is, it has kind of the flavor of Keller-Ricci flow, if you know what this is. And for this, at least for metrics which are compatible with a natural complex structure, then the conjecture holds. Okay, you see that at least just using tools from Riemannian geometry, this conjecture seems to be like widely open. Okay, so what is pluriclosed flow? As I told you, this is a version of generalized Ricci flow which uses complex geometry. So let me go for that. So now I'm going to fix a complex manifold, and my manifold is not going to be Keller typically, because I'm interested in the example of SU2 cross U1 or S3 cross S1. This carries a natural complex structure, but it's a non-Keller structure. So I'm going to use a different type of metrics, which are called pluriclosed. A Riemannian metric G on M is pluriclosed if it is Hermitian. Okay, so J is orthogonal, and omega is DT bar closed. Instead of D closed, which will be Keller, impose this milder condition. And omega is the natural Hermitian form associated to G and J. Okay, so this condition, as I said, is a replacement for Keller. Okay, by a theorem of Gauduchon, these metrics exist on any compact complex manifold, even in non-Keller setup. And if you think in terms of what are the degrees of freedom for these metrics, at least locally, if you have a Keller metric, the degrees of freedom for the Keller metric are functions. Okay, because any Keller metric means a Keller potential, and here the freedom is a 104. Okay, so you see somehow this illustrates the fact that these metrics are more complicated than Keller, okay, because the local degrees of freedom are somehow a vector instead of a function. So let me give you one example, which is precisely the one I'm going to be most interested in, which is the case of a Hopf surface. So you take C2 minus the origin, quotiented by the radial action of Z, multiplying by 2 on each component. Okay, you can multiply by any number, which is any real number. Yeah, there is some condition on the model. Anyway, so what is this? What is this manifold? So C2 minus the origin is like R4 minus the origin. Okay, so this is like S3 times R plus. And now I'm quotienting by a radial action of Z. So what I'm doing is to compactify the radial branch. Okay, so I end up with S3 cross S1. Okay, so topologically this is S3 cross S1, and you can think of this as a group manifold as U2 cross U1. Okay? So if I think of this as a group manifold, I can think of the beam variant metric, and there is essentially 1 up to scaling. And when I write this in complex coordinates, it turns out that it has this expression. So if I write it in terms of natural coordinates on the cover on C2 minus the origin, then this metric, which people in Hermitian geometry call it the Booth-by metric, it turns out to be just the beam variant metric in SU2 cross U1 when you identify these two things. Okay. And then in this setup of compact complex manifolds and pluriclose metrics, Street Santian in 2010 introduced the following flow, which is a generalization of the so-called Keller-Ricci flow. So what is this thing? So I'm going to say that my 1-1 form, my Hermitian form, omega evolves by this ugly looking expression. I mean, the first time I saw this, I thought, oh my God, what is this? And actually when you read it in terms of the geometry, it's a very nice evolution equation. Okay, so you see this bit here. So suppose that your metric is scalar. Okay, just to motivate. Suppose that your metric is scalar, then these two things go away, and this is just the Ricci tensor, the Ricci form. Okay, it's d bar del of the log of the determinant. But this is the way you calculate the Ricci form on a Keller manifold. Okay, so essentially, when your manifold is scalar, this is just the so-called Keller-Ricci flow. And if you rotate by the complex structure, what you get is back Ricci flow up to rescaling of the Ricci tensor by some cost. But now we have this other more complicated expression. Okay, so we have this evolution by the Ricci tensor, by the Ricci form, sorry, of the metric. But we have these other pieces. So when I say the Ricci form, one has to be very careful because we are in a non-Keller setup. So what I mean here is that this bit corresponds to evolution on the Ricci form of the Chern connection of the metric. Okay. And the thing that is going to dictate this other equation is that we are going to use a different connection rather than churn. So some comments is that this is a well-posed problem locally in time as before. So if I fix some initial data in a compact manifold, then the flow evolves for some finite time. So as I said, this morally, at least one can prove it rigorously that at least this reduces to Ricci flow in the Keller case. And because we are evolving by terms of the form dd bar of something plus d bar plus del, if I take del bar of this equation, the right-hand side is 0, right? So at least it preserves the pretty close conditions. It makes sense. So the nice, or the relationship with the generalized Ricci flow is this other result by Street-Santian in 2012, where they show the following. So suppose that you have a solution to pretty close flow, omega t. Then the corresponding metric, the corresponding torsion, so here HC is minus DC of omega t. And the Lie form, theta t, which is given by taking this star of omega and rotating by j, satisfy these equations. So you see, if you drop these two terms, this one and this one, what you get back is generalized Ricci flow, where I'm considering the evolution of the 3 form instead of evolution of a 2 form. Okay. And since you have this one form here, theta sharp means the dual vector field. What this means is really that you have a gauge fixed version of generalized Ricci flow. So after modifying the flow line of the metric by a diffeomorphism, which is precisely given by the Lie form, the dual of the Lie form, then you get back a solution of generalized Ricci flow. Okay. So this is the way this relates to the previous picture. It's a pretty close flow is a gauge fixed version of generalized Ricci flow. Yeah. So more things about this about the general theory for these equations can be found either in this nice paper by Jeff, where he proves regularity results and defines suitable functionals, which are very useful for their study. And also you can find it in this book published last year in the AMS. But now I would like to give you the geometric interpretation of this evolution equation, which looks like a bit arbitrary. So the nice feature or the nice geometric motivation for this equation comes from using this other connection. So instead of using Levi-Civita to define the Ricci form, or using churn in this Hermitian setup, what I'm going is to use this other connection, which is called the Bismuth connection. So if I have a pretty close Hermitian metric, then I can define this thing. This is a connection with a skew symmetric torsion dc of omega. Actually, the torsion is closed because we are assuming that the metric is pretty close, so the dc of omega is 0. And then using this connection and the corresponding Ricci form, one can write the pretty close flow as this equation here. Okay, so this is the evolution of omega is just minus the 1 part of the Bismuth-Ricci form. Okay, the Bismuth-Ricci form is defined via this explicit formula, but essentially or conceptually, what you have is the following. So Nabla-Bismuth is a Hermitian connection. It's a unitary connection in the tangent bundle, and therefore it induces a connection in the canonical bundle. Okay, the curvature of this connection is the Bismuth-Ricci. Okay. Okay, so let me also, this is a technical comment about coupling this with, using the 2, 0 and 0, 2 bits of the Bismuth-Ricci form. It's natural to couple with another form, but let me skip it. It's not very illustrative. So if we consider the problem of pretty close flow by itself, then what can we expect? Okay, so as I told you, pretty close flow is a special case of generalized Ricci flow, or a gauge fixed version of generalized Ricci flow. And since we know a lot of things in Keller geometry, and we have very nice results in the realm of Keller Ricci flow, maybe we can expect to have similar things for this more general flow. So the first thing one can ask is that in a compact complex manifold with vanishing first-chain class, does pretty close flow admit global existence and convergence to some pretty close metric which has vanishing Bismuth Ricci form? And this for arbitrary initial data. This question is a naive cut and paste of a theorem by Zhao in the case of Keller metrics, or the case of Keller manifolds. Okay, so there is a famous proof of Zhao's theorem for Calabi-Yau, for the existence of Calabi-Yau metrics using Keller Ricci flow by Zhao in the 80s, and this is what would you expect, or what I mean. This is the naive statement that you get if you just copy his theorem and replace pretty close by Keller by pretty close. But this is not true. Okay, so pretty close flow does not behave as nicely as Keller Ricci flow. And well, we know this by results by streets, but essentially, let me make it with my hands because I don't have a blackboard here. But what he proves is that there are suitable compact complex surfaces which are T2 vibrations over a Riemann surface of high genus, for which these surfaces have vanishing first-chain class. But the pretty close flow, what does it collapses the fibers to the base. Okay, and what you get in the limit is you need to use Gromov-Hausdorff compactness, but Gromov-Hausdorff convergence. But in the limit, what you get is just the constant curvature metric on the Riemann surface. Okay, as the limit. So this theorem as such is not true, but this is true for Keller manifolds. We see that something new is going on. So the second question is like trying to make this more restrictive, and it's actually related to groups and to the conjecture I mentioned before. So suppose that you have a compact complex manifold with vanishing first-chain class, which carries a Bismuth flat pretty close metric. And then if you have this background Bismuth flat pretty close metric, does the flow converges to this metric? Okay, under some conditions. So I say that this is related to the homogeneous setup, or to the original question that they posed at the beginning, because there is a recent result by 3 Korean mathematicians. I think I don't remember the names at this moment, but what the result says is the following: suppose that you have a compact complex manifold, which is Hermitian, and says that the Bismuth connection, which is Hermitian pretty closed, and says that the Bismuth connection is flat. Then up to finite cover, this is the product of a simple group times a torus. Okay. So imposing Bismuth flat is essentially up to covers saying that you are in a group manifold. Okay, with the invariant metric. Actually, the metric is going to be invariant up to finite cover. Okay, so it's a very specific situation. And now let me make this question even more concrete, because we can now specify to the case of Hopf surfaces as before. Turns out that the Booth-by metric that I presented a few slides ago is actually Bismuth flat. Okay, and can be interpreted as the invariant metric on the group manifold SU2 cross U1. So can we at least prove this long time existence and convergence for this metric here? Okay. And yeah, so the last thing I wanted to mention briefly, I guess I have 1 minute left. Or
Sure, go ahead.
Yeah.
Is this result. So suppose that you have this is a result with Josh Jordan and Jeff Stritch from last year, a preprint on the archive, which is under review. And the theorem says as follows. So suppose that you have a compact complex manifold with vanishing first in class, which carries a Bismuth flat pretty-closed metric. So recall, Bismuth flat is up to finite covers a compact group, essentially with some torus factor as well, with a invariant metric. Okay. So we are essentially in a group manifold situation. Then given a pretty closed metric, omega naught, satisfying this condition in the Dobot homology. So recall that my metric is pretty close. It means that it is DD bar closed. So if I take del of the metric, del of the Hermitian form, this is D bar closed. So it defines a well-defined Dobot class. Then the pretty closed flow with omega, with this initial condition exists for all time and converges to a Bismuth flat pretty close metric. Okay, so reduces question 2 to a homological condition, and actually you can apply it to the case of the Hopf surface and obtain the desired results. Okay. So if I now take the specific case of SU2 cross U1, then I get this result. So if you have a Hopf surface, then given any pretty closed metric, the pretty closed flow with this initial condition exists for all time and converges to a multiple of the Booth-by metric. Okay. So this gives an answer to question 3 and also to the conjecture in the case of the group manifold SU2 cross U1. Okay. At least for metrics which are compatible with a left invariant complex structure. Okay. And without going into any details, I'm away from time now, but let me say that something interesting that happens here. So something about the proof. Okay. It is interesting that the proof uses holomorphic vector bundles. I know some people here know like holomorphic vector. So the proof uses holomorphic vector bundles, and it uses actually the theory of Donaldson-Uhlenbeck-Yau theorem in the non-Keller setup. So the idea is the following. The pretty closed flow can be realized as some sort of Donaldson flow for a Hermitian metric on a holomorphic vector bundle, which is the holomorphic tangent bundle plus the holomorphic tangent bundle. So it's like a holomorphic version of generalized geometry. Say. The holomorphic structure in this bundle is twisted. It's not the direction. And the way it is twisted is precisely via distortion term. The partial of omega naught defines a double operator on this tangent, holomorphic tangent plus holomorphic cotangent. And this is key for the proof. So the thing that pretty closed flow can be regarded as a Donaldson flow in this holomorphic vector bundle is precisely what we use for the proof. Besides the fact that you have this super nice background metric there, but this is the key idea. Okay, so this is all I wanted to say. So thank you for your attention.
Thank you, Mario.
Thank you, Mario.
Are there questions, comments? I wanted to ask about this last comment. So is this a nice metric kind of like a polystable point somehow of the flux in the gauge theoretical setting, or?
Yeah, so what happens is that if you consider the condition of having Bismuth Ricci form equals to 0, then this is equivalent to having a Hermite-Einstein metric on this twisted holomorphic vector band. And this condition here of being Bismuth flat is the same as having connection a holomorphic, having a Hermitian metric on this twisted holomorphic vector bundle, which is turn flat.
Mm-hmm.
So somehow
Mm-hmm.
this is actually an observation by Bismuth in a paper, in a seminal paper in the 80s about index theory for connections with torsion.
Mm-hmm.
So he relates the Bismuth connection, so the connection with torsion and DC of omega in a Hermitian manifold, with the Chern connection on this twisted holomorphic vector band. And this is the observation that we use. So yes, the idea is that any solution of this condition here, this condition here is the more general one that I wrote, gives you a polystable holomorphic vector bundle whose underlying smooth complex vector bundle is just tangent, holomorphic tangent plus holomorphic tangent.
Thank you. Are there more questions or comments?
I have a question. I also have a question, maybe so naive. Mario, can you please repeat how is the pluriclosed flow related to gauge theory?
Yeah, so maybe I can do something. Maybe I can go. I lied to you when I said I don't have a blackboard. I have a blackboard. It's actually fantastic. It's a whole. I mean, this room is amazing. There is this Pere Pascual picture there. I don't know if this was his office at some point or something.
Yeah,
it's a library, and I have this blackboard here.
Oh, fantastic!
So if you make me big, then I can write in the blackboard.
In the speaker view, yes, we can see the blackboard. Yeah.
Yes.
So yeah, maybe like this. Yeah.
Yeah, fantastic.
So what you have is your manifold X.
Yes.
And then you consider a bundle which is tangent 1, 0 of X plus tangent 1, 0 of X. Dual.
Yep.
Okay?
Yes.
The holomorphic structure here I'm going to consider is not the usual one because I have a metric. I have a metric G and the corresponding omega, which is Gj. And I'm assuming that this is pluriclosed. So the DC of omega is 0. Okay.
Okay.
Oh, you see the mirror of my.
No, it's all right. It's just
I'm seeing the mirror of my image. Mirror symmetry here.
Mirror symmetry.
we can see it. Yeah, it's
so
okay.
Anyway, so because the DC of omega, this is the same as y del bar of omega equals to 0, right? And then I can use del of omega to cook up. So del of omega is now d bar closed, and I can use this to cook up a Dolbeault operator.
Okay.
So this Q has a Dolbeault operator which is twisted. It is d bar 0 d bar. So this is like the tangent 1, 0 direction. This is the cotangent. And here I put 2I del of omega. Okay.
Yeah.
So a holomorphic 1, 0 form is going to be a section of this Q, but not a holomorphic vector field. Okay? Unless something funny happens. And now my observation is that, or the observation that we explode in the paper is that writing so Ricci for the Bismuth connection, Ricci for Nabla Bismuth equals to 0, where Nabla Bismuth equals Levici beta plus this is with a minus a half of G minus 1
translation
of omega.
Yes.
This condition here is the same as the Hermitian equation for a metric. So let me define G to be G 0, 0, G minus 1. this is a formation metric on tangent plus cotangent. And now this condition here is the same as the following. The Chern curvature of G in this twisted holomorphic vector bundle, which omega n minus 1 equals to 0.
Very cool. Fantastic.
So having Bismuth Ricci form equals to 0 is the same as this being Hermite-Einstein. And actually, you can make this more precise, because it's not only that the fixed points for the flow corresponds to Hermite-Einstein measures, but actually the flow is just Donaldson's flow for this Hermitian metric.
Right.
And this gives you a lot of information for the a priori estimates in order to prove long time existence and convergence, because you can use all the whole theory.
We can. Yes, it's good.
Mario, this looks very general, and from what you said, it only works for the Hopf surface.
Oh yeah, because the thing is the following. So when we are, for the a priori estimates, we are using this Schwarz's lemma for holomorphic sections of a holomorphic vector bundle, which relates the Laplacian of the norm square of a holomorphic section with some other terms related to curvature. This Schwarz's lemma, we use it to relate some heat equation with something which depends on some background Hermitian metric. If we have a background Hermitian metric which is Bismuth flat, then say the evolution equation the heat equation has no junk on the right hand side, and then you can apply all the a priori emission. Everything follows from some sort of maximum principle applied to the heat equation. Mm-hmm. But if you have no flat background geometry, then things are more complicated. So if you think of, the analog of this proof in the case of Keller manifolds is just the convergence, long time existence and convergence of Keller-Ricci flow on a torus. This will adapt to that case. But for the more general case, the thing proved by itself, this requires completely new tools that we don't know.
Okay, thanks.
So I guess there are no more questions. So let's thank again Mario for the nice talk, and also for making it more live with the actual blackboard.
Yeah.
So
thank you so much, Mario. It was pretty cool.
And I guess I also have to thank the organizers, and especially Ronald for bringing us, although virtually, but back to Costa Rica for a while through the screen. And
you're welcome, actually. We hope next time.
This is it.
We hope next time we can do it face to face in 2024. Thank you so much, Mario. It was amazing. Thank you, all of you.
Thank you.
Thank you.
Alberto, André, Marcos.
Thanks, Ronald.
Marcos. Obrigado, Leo.
Thank you, everybody.
Bye-bye.
Bye.
Very nice talks and very interesting talks. Thank you.